So in this video, we're going to discuss perfectly inelastic collisions. Remember, perfectly inelastic collisions are when two objects with mass and velocity, so they have momentum, are heading towards each other, or one is heading towards the other, and they collide, and after the collision, those two objects sort of crunch together. So after the collision, those two objects sort of crunch together, and they're going to end up with some final momentum. And we can sort of treat those two things as being together, right? As being sort of one object. So the way we can write this, so in this case, we know momentum has got to be conserved, right? Because in any collision, momentum is conserved. And the way we can write that is the sum of the momentum, like the initial momentum, is going to equal the sum of the final momentum, right? And in this case, if we have two objects that are coming together, what that's going to mean is that our mass 1 and our velocity 1 plus, and let's put arrows on these because they are vectors, plus our mass 2, velocity 2, are going to add up to the same thing that comes out at the end. Now, the thing to realize at the end is that we have two masses that are now stuck together. So in order to calculate the momentum of that, we can add up the masses. So we can look at it as like m1 plus m2 times that final speed, right, combined. So really the only things we have here, we need to know the initial mass and the initial velocities, and we need to know the final mass combined and the final velocity. And we can solve for some stuff. And that's sort of the other assumption we need to make, is that these two things stick together, so we can simplify the right-hand side. We don't need to look at these two boxes separately, right? So this is sort of a general equation that we can use when there's two objects. When there's more than two objects coming together, we can derive a different one, but most of the cases we're going to do in this course are going to be two objects coming together. Okay, a pumpkin and apple are launched directly at each other. The pumpkin has a mass of 3.2 kilograms, so I'm just going to draw a quick sketch. Here's our pumpkin, and it's 3.2 kilograms, launched at a velocity of 8 meters per second to the right. So we'll call this 8 meters per second. Now, directions are going to be important here, so we should define what our positive direction is going to be. I'm going to say the positive direction is to the right, as we usually do, right? And then the apple has a mass of 0.15 kilograms and is launched 50 meters per second to the left. Assuming when they collide, the apple gets stuck inside the pumpkin, so picture this sort of messy combination of apple pumpkin, determine the final velocity of the fruits together, right? So we know in this case, we're assuming that the apple sort of squishes into the pumpkin and then they travel together at the end. Now notice a few things first. The apple has a lot less mass, but it's going a lot faster than the pumpkin. So you might want to say the pumpkin right off the bat has much more momentum, but maybe it does, maybe it doesn't, depending on how fast the pumpkin is going. Okay, so let's try. So we know the initial momentum is going to equal the final momentum, right? The initial momentum of all the objects combined is going to equal the final momentum. So what we can do is we can look at this, the mass of the pumpkin times the velocity of the pumpkin plus the mass of the apple times the velocity of the apple is going to equal, and again, at the end, we're going to combine the pumpkin and the apple, right? And it's going to have some final velocity, right, which I'll call VF. So if we're trying to solve, we're basically trying to solve for this, right, VF. Do we know everything else? We do. All we got to do is plug it in and solve. So we're going to have 3.21 times 8. Everything's in the proper units, right? It's all in meters per second, kilograms, so we're good. We don't need to worry about units here. The mass of the apple is 15. Should I put in the velocity? Oh, sorry, the mass of the apple is not 15. The mass of the apple is 0.15. What should I put in here for the velocity of the apple? Well, remember, it's velocity, not speed. And we defined positive as the direction to the right. So we should actually put in negative 15 meters per second here because it's to the left. Okay, let's see what we get. So the mass is combined, so 3.21 plus 0.15 VF. Okay? So if we add those up, or do the math here, 3.21 times 8 plus 0.15 times negative 15. On the left side, we end up with 23.43, and that on the right side, 3.21 plus 0.15 is 3.36 VF, and then we could divide. 23.43 divided by that gives us 6.97 equals VF. Now, two significant digits make sense for this question, so we're going to round that actually to 7.0. And what units is this in? Well, it's a speed, so it's meters per second, because those are the units we were working with in the question. So basically, what's happening here? The final speed is 7 meters per second. Well, first of all, what direction is that final speed in? Is it to the left or to the right? Well, we defined positive as to the right, and this came out as positive. So we know that this velocity is going to be to the right because it came out positive. Also, what happens? We have this apple that's shot into this pumpkin that's moving at 8 meters per second, but clearly the pumpkin has a lot more momentum than the apple does. So the apple does slow down the pumpkin a little bit, right? It slows it down, by 1 meter per second, but still the pumpkin has more momentum. So the pumpkin mostly continues on going along its way at almost its full speed. So there's the solution. If you want to solve this in a different way, you can sort of realize I could have isolated this equation for VF just by dividing by MP plus MA. That's up to you, however you want to do the algebra. And the last thing is, why would we consider this a perfectly inelastic collision? I'll leave that up to you to figure out. Why this example? Why would we consider this a perfectly inelastic collision? Okay? There you go.